Monitoring conditions like diabetes or cancer by taking blood at intervals for testing can miss important rapid changes in blood chemistry. Implants can make continuous measurements, but they are often bulky and difficult to remove and no longer needed. One of this year's TR10 innovators, Frenzo Omanetto, is developing implants made from silicon and sheets of silk, which dissolve away when no longer needed. We asked Omanetto about why he developed the technology and the new types of implantable devices it will enable.
I'm Fiorenzo Manetto. I'm a professor of biomedical engineering and physics here at Tufts University, and I work on high-tech applications of silk. This work is done in collaboration with David Kaplan, who is also a professor here at the biomedical engineering department. And we're specifically working on using silk as a high-tech interface for resorbable electronics. So we want to do electronic components that eventually are largely reabsorbed and reintegrated in native tissue in the body. And this is work that we're doing in collaboration with John Rogers at the University of Illinois at Urbana-Champaign.
The enabler is that you need a material that is highly multifunctional and highly compatible. So the hope is that maybe we found this material. I mean, maybe there's going to be a material that can do these things better. The thing that is actually remarkable about silk processing is really lies in the worm, and it's very unusual how, for example, inside the native silkworm you have this very stable high concentration of protein. Basically, from protein and water, you end up with a material platform of very high structural quality, mechanical strength, and no cracking. Then the handles to actually tune the material property is by varying pH, by varying shear on the way that the fluid is processed, and by varying basically water content. That affects the end product. It affects how smooth the film is, it affects how fast it dissolves, how crystalline it is, how amorphous it is. In a certain sense, you're really trying to be bio-inspired, to have a green processing method that actually ends up with a material that has high-tech properties. And then if you bring in some of the high-tech tools into it, then you add even more functionality.
A lot of the technology that we do in collaboration with the Rogers Group at Urbana is in interfacing thin film flexible electronics, which is a technology that John has pioneered over the past years with the silk technology that we have been working on over the past 2 to 3 years. And so we've taken this technology in two directions. One of the directions is to integrate onto a silk substrate and interface thin film electronics and thin film flexible electronics. And the other thing that we're now combining is the use of is interfacing silk substrates to flexible and stretchable light-emitting diode sources.
The example is that you have a bunch of LEDs of different colors, and each of the connections lights up a different color depending on what the concentration of glucose is, because the concentration of glucose controls the electrical connection between the power source, which we obviously will have by that time, and it's going to be implantable and biocompatible, and the certain color LED. Okay. So something like that, and then you can look at your wrist, and if it's blue, you're okay, and if it's red, you're not.
The particular attributes of these electronic devices and these light sources are that they function when they undergo mechanical deformation, or when they are under some degree of mechanical stress. So you can literally imagine an LED rope that can still function when it's pulled from side to side. The idea that we want to pursue is that since we can interface these light sources and these electronic devices to silk, and these electronic devices and these light sources function as they're being stretched or pulled, is that we can develop conformal electronics that still work very well when they're implanted inside the body, and the body is largely curvilinear and needs some electronic components that still function while they are conformal to certain organisms or certain tissues, and so the utility of this would be to actually have these largely resorbable components that can enter the body and do either electronic sampling or provide light sources, for example, that could illuminate the body from the inside.